This topic is to introduce cyber physical systems or CPS. Before we go into the formal definition, let's just look at this picture first. On the left, we have the cyber side, which consists of processors, data, communication, computation, and then on the right, we have the physical sides, which consists of things like machines, gears, robots, and movement. And what CPS does is it's connecting these two worlds. So now let's look at CPS a bit more in depth. A cyber physical system combines digital components, physical components, sensors, communication, and sometimes even humans into one integrated system. So the keyword here is integration. It's not just one computer sitting next to a machine. The computer and the physical system are continuously affecting one another. So in this table, it gives us a nice way to compare three things. The first one, the traditional embedded system, and the middle one is IoT and CPS. Let's start with the normal embedded system. A microwave oven is a simple example of a normal embedded system. You set the time, press start, and the controller carries out a specific task. It doesn't really need to understand what is happening around the microwave. And then we have IoT. The important thing is connectivity. Devices collect data, send the data somewhere, maybe to the cloud, and then we can monitor it remotely. For example, a smart temperature sensor might send room temperature to your phone continuously. As for CPS, it goes one step further. Now the system doesn't just monitor the environment. It actually uses the data to make decisions and control something physical. So an autonomous vehicle is a good example. It senses the road, detects obstacles, decides what to do, and then controls steering, acceleration, or braking. So a simple way to remember the difference between these three things is that the first one, embedded system, is a dedicated computation mechanism. IoT is about connectivity and data exchange, and then CPS is about sensing, computation, and physical control. So of course, in real system, these categories can overlap quite a lot. So if I have a temperature sensor that only sends data to the cloud, is it necessarily a CPS kind of system? This slide is probably one of the most important slides in this topic. So what you see here is the closed feedback loop. We start with the physical environment. So something happens in the real world, then the sensor measures it. The sensor data is passed to the embedded computer. The computer processes the information and decides what should happen next. And then the actuator performs some physical action. And once the action happens, the physical environment changes again. So the sensor measures the new condition and the cycle repeats. That is why we call it a closed loop. So you'll notice there is also communication network in the middle. That's because in many CPS applications, the sensor, processor, and actuator are not all sitting on the same board. They may communicate over different networks. Now here's something important. What happens if the controller gives the correct answer, but it gives the answer too late? Logical versus temporal correctness. So this is where CPS becomes a bit different from normal computing. In normal software, we usually ask, did the program produce the correct answer? But in a cyber physical system, we also have to ask, did it produce the correct answer at the correct time? And the difference is really important. Look at the airbag example here. A crash happens, the sensor detects the crash, the controller processes the information, then it sends a command to deploy the airbag. If everything happens with the required time, the airbag can protect the passenger. But imagine if the system is slower or a little bit slower. Maybe the processor is overloaded, maybe there is too much network delay, but some tasks takes longer than expected. Eventually, the controller still gives the correct command, deploy the airbag. So logically, the answer is correct. But if the airbag deploys half a second too late, it will be useless. The accident has already happened. So this is the important idea. A system can be logically correct but temporarily wrong. And in CPS, being temporarily wrong can cause physical damage. That's why later in the course, we are going to talk about things like real-time systems, deadlines, latency, scheduling, and synchronization. Because in CPS, timing is not just about performance. Sometimes timing is actually part of the correctness. So where do we actually see CPS? Pretty much everywhere in modern engineering. One big area is automotive systems. Modern cars already have many CPS components: braking system, engine controllers, driver assistance, and autonomous driving functions. Another area is smart environments and IoT. For example, smart grid, traffic systems, and environmental monitoring. Then we have robotics. Robots are probably one of the easiest CPS examples to visualize because they are constantly sensing, deciding, and moving. And finally, medical systems. We can have smart prosthetics, health monitoring devices, and automated insulin delivery systems. The interesting thing is that these applications look very different. A robot looks nothing like an insulin pump, but underneath the structure is actually quite similar. We still have sensing, computation, decision, and physical action. The difference is mainly in what we are sensing, what decisions we are making, and what physical process we are controlling. Now let's look at one complete example. Imagine you are driving and suddenly there is an obstacle in front of the car. The first thing we need is information. So the vehicle may use cameras, radar, LiDAR, and ultrasonic sensors. Different sensors give us different types of information. For example, the camera may help identify an object, while radar may be better at estimating the distance and the relative speeds. Then we combine these measurements. This is what we call sensor fusion. The idea is that instead of trusting only one sensor, we combine several sources of information to get a better understanding of the environment. Next, the information goes to the embedded controller. This is basically the decision-making part of the system. The controller asks questions like how close is the obstacle, how quickly are we approaching it, are we going to collide, do we need to brake. Then the control algorithm generates the required braking command. Maybe it takes to apply 20% brake pressure, maybe 80%, maybe emergency braking is needed immediately. Finally, the brake actuator converts the digital command into actual physical braking. So again, we can see the complete CPS chain: sense the environment, process the information, make decision, control the physical system. And of course, all of this has to happen very quickly. If the braking decision takes several seconds, it doesn't matter how good the algorithm is. This example is quite useful because it shows the difference between IoT and CPS quite clearly. A smart agriculture application. Imagine we place soil moisture sensor around a farm. The sensor collects information and upload it to the cloud. The farmer can open an app and check the moisture level. That's a good application. We are collecting the data and communicating it. Now we add one more step. Suppose the system automatically opens an irrigation valve when the soil becomes too dry, and once the soil has enough moisture, the valve closes again. Now we have a feedback loop. The system is not only observing the physical environment, it's actually controlling it. That's the CPS part. So IoT and CPS are not really two completely separate technologies. Very often, IoT provides the communication and data collection. CPS adds the physical decision making and control. Another thing you can see here is the use of edge processor. Instead of sending every decision to the cloud, some decision can be made locally, and that can be very important. For example, if the internet suddenly goes down and you probably don't want your irrigation system to become completely useless, local processing can make the system faster and more reliable.